Hello students, welcome to EduSil. In this video, we are going to discuss about complexity theory, where we'll discuss about P classes, NP classes, co-NP classes, NP complete classes, as well as NP hard. Okay, these are certain concepts which are really hard to understand, but here in this video, we are trying to make it so easy so that we can understand it better. Okay, so if you're starting this topic, I must say, what is our problem, or why we are just reading those P and P? Without that, can it be easy for us to understand, or can it be skippable or not? Okay, maximum students are really worried about it's a hard topic or is a hard chapter, we shouldn't read that one, or we might skip that one. So yes, of course it will be more interesting if you can understand it better. Okay, so let us have a look here. Why we are reading? The main concept of reading this one is whether uh, like P classes is something which we can really interested to read or not, or whether NP class is really important for us to read or not. It's so simple. Right now our main target is to focus on a problem. Clear? So as algorithm we are having, like we read algorithm, we are reading algorithm. The main concept of reading algorithm is like whether we can give a proper solution to a problem or not. Okay, that's why we are reading the algorithm. The simple definition for algorithm is like we have certain steps, certain solution steps which gives a proper solution to a proper problem, or might be to a particular problem. We have certain solution steps that we have written, which is effectively utilizing the artificial resources like our time and space. This is what the algorithm is. The solutions, steps, everything that we have discussed in the introductory chapter of algorithm. Those who are new, kindly watch that one. So before that, we should know whether the algorithm is written. Before that, we should know what is problem. Clear? So the problem, you can check. I have certain slides for you, so where you can understand like what are solvable problem, unsolvable problem. Before that, we should discuss about a problem. Problem is anything. Anything in the world is considered as a problem. Like you need, like you are in summer right now. You need AC to be installed. Definitely, it's a problem. If you are installing the AC, definitely you are getting might be the temperature is low, or for that reason suppose you are using any machine to get the work too easier. Definitely you are providing a solution which the AC or might be the machine is working as an algorithm for us. Clear? Like a problem could be anything. Suppose my problem, I'm just thinking like I should close my eyes, like I'm on the earth. Okay, I'm closing my eyes. If I open it, I should be on the Mars or moon or anywhere. Okay, is it possible or not? That we should think of. But problem is a problem. So whenever we are deciding of for the P or NP, before that we should know where it starts. Clear? So before that we should know what is a problem. Problem could be anything. Okay. From that problem, whether we can create, whether we can have a solution or not. If we have a solution, then we can go onwards. Okay. If it is not having any solution, like you could say it's unsolved problem for us, so in that case, we first segregate the problem into two different halves. One is unsolved, another is solved, or have solution or doesn't have solution. Clear? So those concepts we should have to clear enough. If we have a solution, then we can make it so effective. Clear? That's we have already studied about it. Okay, if it is solved, so definitely we can say there is an algorithm exist. Why? Because if it is solved means we should have a solution for us. So if we have a solution, we should have to write the solution steps. The solution steps comprises of the algorithm. Okay, so here we can focusing on algorithm. But if it is unsolved, like if it is not able to solve for the time being. Clear? Suppose I'm just saying the same example, I'm repeating again. Like if I want to close my eyes on the earth, if I am opening my eyes, I should be on the Mars or on the moon. Clear? So in that case, what will happen? So it is not possible right now. It might be possible after 100 years or might be 1000 years. Clear? But it is not possible right now. So what we have to say, unsolved problem, we are not focusing here in NPP classes because we do not have any algorithm for that. If we do not have any algorithm, so why should we focus here? Clear? So right now we should have to focus on the solved problem. So to make it easier, I'm just having one example in a GIF format. Because what are the solved problems? Suppose I said, so what you have to do, like you zoom in your camera and you zoom the image of the moon. Okay, is it possible or not? It's a problem. So the solution is yes, we can zoom it. Clear. Unsolved problem is like I want to run the vehicles or cars, whatever you want to, just have a race on Mars or Moon, wherever it is. So is it possible or not? Definitely no. It might be a problem, but it is not possible at all. So this is considered unsolved. So we are not working on unsolved one. Though we have a solution, so we are working on the solved problem rather than working on the unsolved one. Clear? So I hope it is clearly understood by you. Then from solved, I'm just writing it, from solved problems, we are working with tractable and intractable problems. So what is tractable, what is intractable? Before that, we just have a look here. What is complexity? Like as you have already discussed with the computational complexity, you can say the complexity is big O. We are just writing it's a unit for us. Okay, so constant is less than big of log n or log n. We have already have a videos. Those who are new, kindly watch the previous videos. We have discussed it. So next is I'm just making it so simpler for you to understand. Okay, so here is big of n to the power k, where I'm just writing it where, or might be you can say where k is greater than 1. It can be easy like big of n is equivalent to big of nk, where k n equal to k, so it will be similar, but I'm just making it just uh, uh, as for the NPP concept. I'm just deciding that one, like how we can be making that one n factorial. Next we go n to the power n, which is considered a super polynomial for us. This is super polynomial, this is factorial, and this is k to the power n, means k is constant here, and n, as we are taking n. Clear? So k is constant. I must write this, k is constant. Constant means you can take 2, you can take the value of 3, you can take the value of 4, but here the constant should be one time that you should have to focus. K should be more than 1, where this must satisfy. Then only we can say it's a uh, exponential for us. Okay, this time said to be exponential for us. Exponential. It is factorial. It is super polynomial. It is polynomial for us. It is a linear for us. Logarithmic. It is constant for us. So we had a discussion on earlier videos. So constant could be big of 1, could be big of 100, anything. If it is a numeric value we are having, so we can say it's a constant for us. So logarithmic, the number of logs you are introducing is definitely less, but it is somehow higher than the constant. We had already discussed on this. Up to this, what I'm saying, up to this, we are just thinking some problem which are having a solution in based on basically we are focusing on the time. So here the computational complexity having space and time. So we have definitely two you can say two different types of uh, solutions for us, two different kind of artificial resources we have used, like one is time, another is space. So here we are discussing about the time and as well as space. So whenever we are discussing on the time and space, if of two polynomial we are having like n square, n cube, whatever the value, but it should not be equivalent to n. Okay, so k should be less than something which should be not equivalent to n, but the value is constant. Okay, n square, n cube, n to the power 4, n to the power 5, whatever the values we have. Clear? We are considered these are the polynomial time for us. And from this to super polynomial, we say as something, first of all we decide as tractable and intractable means. Tractable are easy problem for us. Okay, I'm just writing this. Tractable means which are easy for us to understand, easy problems or easy solutions. Better we should discuss that one, having easy solutions. Easy solutions like we can decide that one as well as we can verify that one. Okay, you can write uh, decide and solve. Better we can write it solve and verify, means we can solve that within the polynomial time. Here also verify polynomial time. Intractable is not so easy, or it's better you can say it's a hard a solution where we can say it's might be more than the polynomial, or you can say the better time complexity is considered as n to the power k. Here also verified with n to the power k. Here the concept we must write is big of n to the power k, verify also big of n to the power k. Why I am writing in this order? Here you just think big omega is considered as the best time complexity. Okay, so whenever we are deciding like 1 to 100 and from 100 to 1000, so to write it, what we are writing, the starting point when the best is 100 for us, so we can write this as in this order. Okay, like we can have the time complexity no doubt as a polynomial, but this is a best time, but we cannot always guarantee about the best time complexity in intractable problems always. So maximum time it is named as something like NP complete or NP hard, that we'll decide. But before that, what is tractable and what is intractable problem, first we'll complete it, then we can go towards the P, NP, whatever are there. Okay, so if you're writing in between the range, you must write in this order, or if you want to represent that, you might say like this is the way of representing the values. Like upper bound is means maximum time complexity you can expect is 100. So this is what we have written. The solution is n to the power k. No doubt if you're getting as a constant also, that is considered as a easy solution for us. But maximum is n to the power k. And here in hard solution or might be intractable problem, we will expect the best solution as polynomial, but the maximum we can expect is big of n to the power n. I must say the maximum time complexity we can expect is n to the power n here. Okay, this is how we can represent it uh, to uh, to provide a better uh, time complexity or a better complexity theory for the tractable and intractable problems. Okay, so I hope it is clearly understood by you. Okay, and for computational complexity, as we discussed earlier, so we must say it's a tractable problem lies between these two. That means it's a upper bound means the maximum we can expect is this. That's why we said this as maximum complexity, and here the maximum is this. But for minimum, if I can say minimum, that we started from here, so we can represent that is you go into the power k for intractable problems. For intractable problems, I hope it is clearly understood by you. Like we have to first segregate what are the solvable problems. If we solved it, like then we decide, like then we go in detail about tractable and intractable based on the complexity which we have already completed. So this is what we can say. No doubt n to the power k if I am writing as 1, also we can consider it as a linear, but that linear is also named as polynomial, no doubt, because within that we are expecting that one. No? So that's why we are saying it is linear for us. Okay, computational complexity we have somehow completed. Now we will go in detail about P and P. Before that, we should be discussing about what is like on the upper bound for us. I'm just changing it, but if you'll go in detail, might be it will have something different. I'm just writing it. Always space is greater than time. We should have to know that one. Here is P. Okay. So whenever we are discussing XP space means exponential space. EXP stands for exponential. Okay. Like we must say that one is k to the power n. Okay. This is what are exponential. And P space is polynomial. P stands for polynomial, which is big of n to the power k, where k is constant for us. Okay. Next, NP stands for non-deterministic polynomial. Non-deterministic polynomial. Now I'm just writing the definition. I'm just writing like why we are saying this is XP, what represents the P means. Okay, we discussed that one. Right now our target is what is P, what is NP, what is P space, what is XP type. For this video, like we are having the introductory one, so we are just touching each point. Okay, our main target is to know P, NP, and NP hard, co-NP, NP complete. These are the concepts to know. P classes, I'm just writing it, solved or solve. One is verify. For P and for NP, first we have to write that one. If you can add co-NP also, we can write further. But first of all, we should write it when we say it's a solve like P class for us. If it is solvable within polynomial time and verified within the polynomial time, then only we can say it is polynomial time for us or easy solution for us. Sometimes we can say it is easy for us. Okay, and sometimes it is said to be not easy to solve but easy for verification. So solvable is unsolved or might be cannot be guarantee about the solution, but we can say the verification case it is polynomial for us. So sometimes we can say verifiable is in polynomial time, means we can verify any problem. If it is verified by polynomial time, we can say it is NP for us. Don't worry, I'll have certain example, better example to like give you like idea how we can say it is NP or not. Okay, so first of all we should know it is verified by polynomial time, that's why we say it's NP for us. Clear? So I have kept one example for you to understand. Okay, so though p is easily understood by you, like it is solvable by polynomial time, and also verifiable with the polynomial time. I must say, before reaching that one, suppose I have a problem. Okay, whether I'm saying you can say to find prime or not, prime or simple, like odd or even, odd or even, whether a number is odd or even. If you want to find it out, like is it so easy or not? Like we can divide by 2, we can have to verify. Okay, we have to divide it and we will be having the verification. Suppose if number 4 is divisible by 2, so we must say yes, it is divisible by 2. We can check the remainder part of it, like we can say percentile 2 equal to 0, like remainder is 0, which is a code that we have already written so many times. To find whether a number is even or odd, we are just taking that one and we are just checking with, is it 0 or not? Is it too easy for us to find it out? So for solving also, it is taking just big of one. We are taking the within that for loop, whether it is or not. For loop is taking big of one, so solution is also big of one. And to verify that one, like verification means, like we are just doing from our end. Yes, it is verifiable. Verifiable means you just take an example for that. 2 into 2, clear? So 4, the remainder is 0. Now you can verify, yes, of course. To verify also, it is within the range of polynomial, means it is not equivalent to into the power k, less than into the power k. That's our upper one. We have set it maximum it can reach to the polynomial one, but less than that is also considered as a solution, easy solution for us. So this problem is a part of p. But whenever I am discussing about the this one, we have a jigsaw problem or a puzzle problem. There are many certain uh, small pieces of puzzles are there. So we have to check, like here two different, you can say here one and two, two different positions we are having. Like we have to check with the probability. Like if you can have two different, suppose this type of uh, like here, as for the example I'm just keeping here, like suppose this type of two, suppose this is one and this is two pieces we have to first check it. Like we cannot directly merge it whenever we are providing a solution. So we have to verify it. Whenever we have to verify, like we have a samples for us, and within that we have a number of pieces which has been attached. We know if it is at here as an example, we have different pieces, like 4 pieces we have. Once we attached it, we have to verify. It is too easy for us to verify, yes, all the pieces are clearly attached or not. Once it is completed, okay, after completion we can verify it easily. Like with the samples we can have to check it with the sample, with the solution we can verify it. But whenever we are attaching, if the number of nodes here as 4, means number of pieces are 4, so that it's easy for us. Suppose the number of pieces are 1000. In that case, whether it is easy for you to solve that one? No, never. As compared to 4 pieces, 1000 number of pieces you have, so can you solve it within 10 seconds? Never. But 4 you might have the option. Number of pieces increases, so number of complexities are increases while solving it. But while providing the verification, it is too easy to verify. Like here, the sample you have something, and there you have another solution which you have already got. So the verification here I have written, the verification is easy for you. Verification is easy, but solution is not easy. It is not easy. Why? Because depending on the number of pieces, as per the puzzle, jigsaw puzzle we have. So how we can do that one? If we have two different, you can say here two different like pieces with the two different shapes or sizes. So whenever we have to check that one, we have to rotate it. We have to check, no, it's not. Then we have to rotate. You have to find a way. So whenever we are finding the way for the two, you have two different check words. So what you have to do is 2 to the power n into n factorial time it will take. Okay. So whenever you are solving that one, as for the ideal case, jigsaw puzzle, having a piece of four different size, four different pieces, like four different, you can say this one, like here we having two here. So in that two, instead of two, in general ideal case we are having four. So in that case you can expect 4 to the power n into 4 in factorial. It is taking more than a polynomial time to solve, but it is verifiable within the polynomial time. That is what the NP is. Okay, non-deterministic polynomial time means we can determine it using non-deterministic motion. You can read it in theory of computation. Okay, so I hope it is clearly understood by you, like why we are saying it is NP. We can verify it easily by looking at, once it is completed we can look it, even if the anything which is verifiable, like we can verify it within the easiest manner, like big of and the k, we can say it is NP for us. Okay, but solution you cannot guarantee about. Okay, so to make it more clear, I have said it earlier. So P and NP, I'm just writing it again. P for solution, whenever we are solving, it is easy for us, easy to solve. And whenever we are saying as verification, also it is easy. Easy means it belongs to n to the power k or n to the power k. Okay, but for NP, non-deterministic polynomial, we cannot guarantee about easy. It may be easy or may not be easy. That's why I'm just writing in this way. Okay, but here verification is easy with big of n to the power k. Whenever I am introducing co-NP, the problem arises. What are the problems? For NP, whenever I am deciding with NP and co-NP, suppose you take an example of, like for yes answers, there are two different, because this is a part of decidable problem. Decidable problem. For decidable problem, what are the issues like we have? Like for decidable, like we can write an algorithm, we have certain solutions for us. Okay, so decidable means for decidable either yes or no. For yes answers, for yes answers, if it is easy to verify, we can say it is NP. For no answers, here also for solutions, we have a doubt. We have a doubt whether it is easy for us or not. We cannot guarantee about. But easy solution we will be having. But it is a complement. Co means complement to NP. Complement or negation, you can say, if we have certain x there, so here we can say it is x dash or x prime. Sometimes we can say it's a prime NP also, but complement is too good, so that's why we are writing co-NP. So for no answers, suppose we are finding whether it is possible with no different cases or not, or yes different cases or not, like though it is a part of decidable problem, so we can say no answers, like no such objective. Suppose our objective is to find no data are part of this. Clear? No data are the part of this. If you want to verify, it is too easy to verify. So definitely we can say it is a part of co-NP. But in general, we are working with NP and P. Okay. So whenever we are just discussing about NP and P, there we are focusing on the verification. Okay. If we introduce co-NP, so no type of answers we are finding, suppose negation of answers or any kind of answers which are opposite to NP, if we are deciding, so here the verifiable or the verification is easy for both NP and co-NP. Clear? So I hope it is clearly understood by you, like what is P, NP and co-NP. So for an example, I must say, so first initially I must say P is within that NP. Why? Because it is not decidable. Okay, decidable within easy or not, but P is decidable as well as verifiable. That's why it is within the NP. Sometimes we can say whether it is easy or not. If NP and co-NP is easy, then we must say NP equivalent to P, but sometimes it is not always. So for co-NP and NP, I must say there is a relation like this, co-NP and P. If you are writing co-NP, if you are introducing co-NP, so P will be the part of it, part of both P and NP. Okay. So here the intersection of NP and co-NP is P. But in general we are not deciding that one. Okay. So now for NP complete. Okay, if we include NP complete, we should know which one we should discuss about NP complete. Okay, NP complete and NP hard. Certain problems we are having, like you can say, best problem for NP is uh, certain SAT problems, satisfiability problem, are a part of NP. Okay, but suppose you are finding out Hamiltonian path. Okay, for Hamiltonian path or Hamiltonian cycle, so you can say Hamiltonian path is a part of. Uh, you can say suppose you're finding whether there is a cycle or not, cycle or not in Hamiltonian cycle or not in Hamiltonian cycle whenever you're finding suppose Hamiltonian graph or might be circuit or might be suppose whether there is a cycle existing in Hamiltonian cycle or not, suppose you're finding out. So whenever you are finding the Hamiltonian path is somewhere you can say also whenever we will be discussing about the reduction, that time we will decide about like how Hamiltonian cycle is reducing the problem from cells traveling salesman to the Hamiltonian whenever we are doing the reduction. That time we will be better to understand like how it is being done. So till that, first of all, we should know what is Hamiltonian. In general, Hamiltonian is like you can say the nodes visiting for one time. The nodes visiting for one time. If you'll be having the path from where you have started and that particular point you are ended with, so we can say so Hamiltonian cycle could exist. But for the path, if you're not reaching to the point where you are actually started and every vertices is completely visited, that path is considered as Hamiltonian path. For Hamiltonian cycle or path is a part of NP complete, and NP hard is to find whether cycle is present or not, or you can say cycle or path also we can say is a part of NP complete. Sometimes some are saying Hamiltonian path is a part of NP, but it's a problem where we are finding whether all vertices is visited once or not. Okay, so as for the definition, we must write NP complete or NP hard. Basically, we are writing is a hardest problem or a set of problem which is a part of hardest problem, hardest set of problems also we are writing hardest problem in NP. NP complete not hard or not easy you can say, or range in between NP and NP hard. Okay, so it is in between NP and NP hard. we can say it's a complete for us. Sometimes example I'm just giving you the better example, you can be easily understood. Okay, so NP and P, if we can distinguish, suppose you can say we know headshot. Okay, in general we are playing too much games. Okay, so just one. There are four examples I'm giving. Okay, you can say the example. As for the example, how we can detect it. As example, one is first example, second, third, fourth. There are four examples I'm giving you. One is you, another is as we are introducing shooter, so you can say expert shooter. Okay, suppose in the first case, as per the probability we are deciding now. Okay, you use whatever we have studied, now we are summarizing that one in PNP and NP complete with the NP hard. Okay, so just listen carefully, this is a summarization of it. You want some expert shooter, you can say expert shooter or expertise in shooting. Okay, probability, suppose I am saying the example is like one person is standing, you have to do the headshot only, headshot. Okay, so what you have to do is like you have to touch the head, the gun point should be in a head part. Okay, the first is like whenever you are shooting, clear, the first of all your target is headshot, headshot is our target, and you with the expert, you just touch the target person, the head with the gun should be touched. Okay, the first case, so the probability definitely to have a headshot is 1. Clear? You have touched it here and you can definitely click once the target, definitely the headshot is probability 1 means definitely yes. Okay. Whenever you just think some 10 meters, here 0 meter, here 10 meter, the range is 10 meter now. The target is standing 10 meters far from your location. Okay, so in this case, your probability is definitely 0.5. Clear? Or might be if you can think it's a standard. Okay, might be it's stood something. Some you can say the target is just stood far from your location to 10 meters. The probability is reduced to half. But here the probability is reduced to 0.9. Might be just little bit. Okay, though he or she is an expert, so definitely the range will be fine. Okay, suppose you can say 10 meter with direction plus direction. Okay, if direction is added with 10 meters, the probability is definitely less. You can say 0.2 because you are new, you don't have any like the knowledge, shooting knowledge you have, so you just like there is a direction from left to right, like you have played a game, so your target is moving from left to right, again from right to left, again left to right, but it's have certain direction and 10 meter is a range, so probability is definitely reduced because you cannot do the headshot. In that case, expert, the probability is reduced somehow, zero point 0.7 or zero point 0.5, you can say, suppose zero point 0.5. Clear? Expert, but it is reduced somehow. Clear? So in that case, we will have the reduction of the probability to have the proper solution, to have the proper headshot. Okay, for fourth one, the example is the direction is having a single direction, here 10 meters plus haphazard movement, or you can say zigzag direction. In that case, definitely your probability is nearly about 0.001, or which is probability 0. You cannot guarantee about. I must say it's 0.001, which is negligible. Okay, you cannot do the headshot. Why? Because zigzag manner, sometimes he or she might be whatever the target is, sometimes he stopped or might be she stopped. Okay, or somewhere they can manage their own timing. So here in that case you cannot shoot, you cannot do the headshot properly. Here in this case, to have this one might be probability is 3 or 2.5 something, because though he or she is an expert, So the probability is reducing based on the zigzag direction. Okay. So in this case, the P class is this one is a P class for us. Both of us, like for our comparatively with the expert, we can decide our problem. Okay, it's a solution, it's a predefined solution with the ideal solution we have, but based on that, what is our solution we are getting is probability one, because we touched it and we get it the easy for us. So easy means P class. Sometimes it is reduced now, so it is non-deterministic polynomial. Sometimes we can sort it, sometimes we cannot. Okay, so in this case we can say it is NP complete, and sometimes NP hard. NP hard and NP complete. NP hard means though it's a zigzag manner, so whenever we sort it, we cannot guarantee, like, yeah, it might be a target for us, or like targeted sort for us or not. So it's NP hard, or definitely between NP and NP hard, which is ranging for us, we said it's a complete for us. Okay, so this is a proper example to decide. We have a solution. Based on the solution, the complexities, based on the complexities, or based on the probability of getting the solution, we have decided like which is a part of P, which is a part of NP, which is a part of NP complete, which is a part of NP hard. Okay, I hope it is clearly understood by you. If any doubt you are having, comment below, and the next video we will be reading about the reduction. So I hope it is clearly understood. Thank you. Have a good day.